Just a little bit of background for me. I've been with Wolfram for about 3 years now, and I've spent a little over the last decade in chemical education and a little over 2 decades doing computational chemistry. So with that, I welcome you. It's good to see you, but I'm going to turn off the video so that we can focus on the presentation. Great. All right. So today we're going to focus on strategies for building educational activities that work in the modern environment of in-person, hybrid, and remote learning spaces. So this has been a challenge for all of us over the last year and a half, and will presumably continue going forward. So I want to show you some of the ways that I've used the technology in my own classroom and others have used it in theirs. So I'll be talking about the following 6 areas of tools. So last week we learned about the Wolfram language, and Arben introduced us to getting started and basic syntax and using the notebook environment. I'll continue today with giving a more detailed description of some of the chemistry-related functions. We'll also talk about the functions that are in the Wolfram function repository, which is a user-generated collection of functions that you can use right inside of your notebook. The virtual chemistry laboratory is a collection of 4 laboratory activities with instructor materials and such. We won't have too much time to talk about that today. The link is available in the notebook, so I encourage you to check that out after the session today. The Wolfram demonstration project is a house for manipulatives, interactive demonstrations of various chemical concepts and many other disciplines for that matter, but we'll focus on the chemistry content today. And then of course there's Wolfram Alpha, which is the website, also available via a mobile app. And then we'll talk about Wolfram Alpha Notebook Edition, which is a new form of notebooks that allow you to do Wolfram Alpha calculations, multiple Wolfram Alpha calculations in a notebook environment. So moving right along. When you're designing new activities for your classroom or your learning space, and you're incorporating a new technology such as digital technologies as a notebook or such, you yourself are going to have to get up to speed on how to use the technology, and therefore so will your students. And whether your classroom is a flipped classroom or otherwise set up, you're going to need tools that help get everyone up to speed. And we have some of those available. We have videos for short introductions, literally under 2 minutes, for putting together queries for using Wolfram Alpha. In this case, we demonstrate a mole to mass conversion, which unit conversions are so common in the introductory chemistry curriculum. And then, of course, we'll show you how to do a balancing a chemical equation, getting the syntax of how to put that into the tool, and then, of course, doing stoichiometry with a chemical equation as well. Besides those videos, we also have written documents that go into more detail with demonstrations of, again, how to use the queries for Wolfram Alpha in a chemistry setting. Most recently, we have a tutorial on using the math step-by-step, so the math tools of Wolfram Alpha to help you your students get ready for their introductory chemistry course. And then, of course, we have a 4-part series here going over 4 major areas of chemistry and using Wolfram Alpha to help in the problem solving that you run into in these areas of chemical reactions, chemical solutions, structure bonding, and then quantum chemistry. So those are all available on the web. You can link them into your learning management system or embed them in sort of PDF document, depending on how you disseminate your materials in your classroom. So besides getting your students and yourself up to speed with the technology that you'd like to implement, you also need to be able to get access to high quality chemical data. The periodic table does not contain everything that one might need to solve chemical problems of interest. whether that's a research interest or a educational interest. And not everyone may have access to the CRC online or other chemical data resources available that you might have access to on a campus environment. So inside of the Wolfram language, and inside, therefore, notebooks in Mathematica, we have a system for interacting with data that is in the knowledge base. That system is the entity system. And the entities for chemistry cover 3 broad areas. The elements, of course, a little over 3,000 isotopes, and over 44,000 chemicals. Now, as many of you know, there's more than 44,000 molecules that one could think of. But at least for the education purposes and a decent start at research purposes, that 44,000 should get you going. And it's curated information of structure, melting points, boiling points, molar masses, all that good sort of stuff. And you might be concerned that, well, is it okay, or how does it relate to switching to an electronic model where students are pulling up data either in a notebook from a curated database rather than possibly going to a CRC, either digitally or in hardcover? And here's where the American Chemical Society on Professional Training, the group responsible for setting the accreditation requirements for collegiate chemistry programs, has something to say and guide us on. They emphasize that students should be able to locate chemical and physical properties of substances. They should be able to search by molecular name, and they should be able to collect that data and archive it. Having good data management, not only that they can themselves work through the problem or a series of problems, but also share that information with others. And then, of course, not surprisingly, there's interest in having the students be able to properly cite reference data. Our chemical data has come from a variety of different sources, and you can get the source information either by going to the reference page for elements or isotopes or chemicals, or you can get that information out of a Wolfram Alpha query. I'll show you in just a moment. So we don't have just one source. We have a few sources that the data inside of the Wolfram language has been pulled from. So we talked about last week the control plus equals syntax, where you bring up this little input dialog in your notebook, and it allows you to give input that is then interpreted and converted into the Wolfram language. And so I think that's one of the easier ways to get into the entity system. And so I'm going to show you how to use that here. So I've done the control equals already, and then I'm just going to type stannous fluoride, which is a molecule that shows up in my toothpaste. And as you can see here, you get the proverbial yellow box pulling up. It's saying it's a chemical. And you have a checkbox to accept this interpretation, which I'm going to do. So now I have the object that represents stannous fluoride from the knowledge base. And now, using the syntax of open square brackets followed by the bit of information that you want, and you can see that we get auto generation of lists of things that we can ask for, the molar mass, and it comes right back out. And we don't have to just work with stannous fluoride. We could look with, say, sucrose. We could ask for the color structure diagram out of the database. We could get that. So variety of different ways of interacting with the entity system to get information out. And we can get properties, whether they're structures or molar masses, and that same information can be gotten through a Wolfram Alpha query. And we can do Wolfram Alpha queries inside of a notebook using the function Wolfram Alpha. And I'm going to use the function grid to set up 2 outputs from Wolfram Alpha side by side. And the inputs that I'm going to give are caffeine and spelling right. And then I'm going to give a favorite molecule of mine, uranyl dihydroxide. And we pass in the alignment equals top option so that everything shows up in the grid, top of the grid, as we would like. So that goes off and does the queries, and then is going to put them out for us. So again, alpha is available on the web or the mobile or in notebooks. And what I wanted to show here is that for caffeine, which is a molecule of that 44,000 in the knowledge base, we get quite a bit of information. Quite a lot, actually, in each of these pods. And each of these pods are available should you want to use just one of them. You could click on the plus sign and stick that in your notebook to make available to your students. And again, quite a bit of information from the curated knowledge base. But for molecules that aren't there, such as this uranyl complex, then we still provide a computable information such as the molar mass, of course, the formula, elemental composition. So you can still get information even if you've got a structure that's not in the knowledge base. And we'll talk about how to do even more information if we pass in, rather than a formula, if we pass in the systematic IUPAC name to the molecule function later on. We'll come back to that in a minute. So in the case of designing your activity for the classroom, you now have the ability to have your students access through Wolfram Alpha or the function inside of a notebook. If your classroom has access to Wolfram Alpha notebooks already, then they get access to this information without having to go to, say, for example, a CRC or search through various sources on the web. It's right there ready to go to do calculations with. And we'll come back to show how you can glue those bits together in an activity a little bit later. So in the chemical education community, getting our students to get to fluid chemical thinking and deep experimental design questions is sort of the holy grail. We want our students to be able to think like chemists, and we want them to be able to talk about experimental design and how to modify existing experiments to get different information or improve the results. And that can be very difficult to get to in the curriculum, particularly if you're working with students that might have some difficulty doing calculations. And so depending on your curriculum goals, chemical calculators can come in to help that. So I'm going to load up two Wolfram Alpha chemical calculators while we let that run. So the nice thing about a calculator is that once a student has demonstrated a particular calculation, such as dilution, in a separate activity, they've shown they've known how to do it, then if you have a calculator that they can use to do that calculation faster, that allows you then to build activities that dig deeper into other topics rather than being slowed down and hindered by the cognitive load of having to do that calculation that they've already shown that they've mastered. Conversely, if it's okay in your particular curriculum that the calculation of dilution be done with a calculator and the students don't have to show mastery of that, they just need to know how to use a calculator and then go forward. This could be helpful possibly in a health discipline where deriving the formula and setting up the calculations is maybe not necessarily as critical as the applied application of that. So here we have nice examples of two of the many calculators that are available. So we have the dilution calculator. It's pre-populated with some initial concentrations and initial and final volume. You can put in your values and hit compute, and it'll recompute what you've got. So we could change this to, say, 6, and maybe we'll put this at 0.4, and our final volume we'll do, let's say, 2 liters, and then you hit compute. And so that's evaluated, and after the results come back and tells you the final concentration in a couple different ways, a couple different units, excuse me. And here we have a step-by-step solution button. We'll come back to this in just a moment, but do note that that comes out in the result pod for the calculators, as we'll see in other queries as well. And so the other one that I have loaded up here is the Beer-Lambert law. Again, you have your input fields. The students can put in their values, hit compute, and get out the calculation solved for them. Other pods that come out with the calculator, such as this diagram, can be helpful, showing what all the different things are. And again, if you want that particular pod in your notebook, if you're building a notebook of examples and a tutorial of different things, you can click here and get just the input that generates this diagram by itself. So you can use these as a collection or use them individually in your design of your activities. Now, we have more than 2 calculators. Those are just the 2 that see a lot of activity, the dilution particularly outside of chemistry and biology and the health professions. But we have over 50 calculators spanning quite a few topics in the chemistry curriculum, and not only spanning topics, but also spanning parts of the curriculum itself. So we have calculators for things that you would run into in your first year courses, your second year courses, in Orgo, and upwards into inorganic and PChem as well. So again, all of these calculators can be used in combination with a larger activity to reduce the cognitive load that the student is carrying to, as I said, get to deeper thinking questions that we really would like to have the students get to in their activities. So again, when you get the notebook from the session at the end of the session, each of these is a link to the corresponding notebook, or excuse me, corresponding calculator, and you can check those all out for your use in the activities that you're doing. Well, generating activities, regardless of where you are in the curriculum or the discipline that you're teaching in, it becomes tricky to generate all of those customized activities, specifically if you're in a remote learning environment where you have to be cognizant of students interacting with each other in a way that you may or may not want for your particular classroom, or if you're doing an online assessment situation where you need to have everyone have an asynchronous, not asynchronous, but a different exam so that you're reducing the temptation for cheating and such. And so generating those different assessments is tricky in and of itself, but then coming back and generating solution keys for that so that the students can work through their answers and figure out where they went wrong on their own can be a large lift as well too. So that's where the step-by-step solutions come into play. And the step-by-step solutions are auto-generated answer keys for particular problems. And so here I've loaded up 4 different alpha queries: chemical conversion, a balancing of a chemical reaction, and then 2 other questions asking based on a chemical equation that was given. So asking for the rate of reaction expressed and asking for the equilibrium constant expression. So as you'll notice, in each of the results pods, you get a step-by-step button. And this step-by-step button can be pressed to pull up the custom answer key. So I'll go ahead and click those and get them going. And again, these are being generated live on the fly, and they respond to whatever the query was. So if you have a different concentration in a different aliquot and a different molecule, that all is taken into account and dealt with on the fly. So the step-by-steps are, as you see here, they start off with a restatement of the problem so that it's clear what's going on and what you're trying to solve for. Here you're trying to balance the equation. And then in both of these cases, they dive right into doing the calculation. So here we have to convert the volume, and we introduce the variable, and we do the conversion using the common dimensional analysis notation. Watching for sig figs, we gather the other bits of information that we need. We grab the formula that we need and we plug everything in, and then that gets us to moles, and then we get the conversion factor from molecules to moles, and we set everything up and have the solution. Likewise, for balancing, we use an algebraic method, not surprisingly, since we're in the Wolfram language and it does so well with mathematical systems. And so we set up the expressions and solve and return the results as you would see them typeset in a notebook or a textbook for that matter. So here we have like I said, the auto-generated answer keys, which One can get access to using Wolfram alpha calls. And as I said, you could get just the answer keys themselves as a pod to paste into an example in a notebook that you're creating for a particular topic or activity. Those can be put right there. And of course, they're available on Wolfram Alpha, the website. Now, with the expressions here, they're slightly different in the sense that you're building, well, first of all, you're building up an expression rather than evaluating it. But they also show a different feature of our step-by-step offerings. And that's namely that we give a plan step where we lay out a plan for solving this type of problem. And the plan step is there to reflect what we do when we're designing an experiment. We have to stop and think about what we want, how to get there, and lay out the steps in the experiment. And we reflect that in our step-by-step pedagogy, which is also reflected in modern textbooks these days. Their problem solving often involves a starting step where you plan out what you need, gather your data, and then solve the problem, rather than trying to solve it on the fly, remembering different steps as you go along. There's this planning stage, and we have that here. And so the plan is a bulleted list that gives you a framework for solving rate of reaction expression problems, setting up the rate of reaction expression. And again, just like we saw before, it steps you through. First you balance, then you take those balance coefficients and get the stoichiometric numbers, and then you go ahead and set up the various expressions that you need, and then you plug those in for both cases. Now, with the equilibrium constant, since the symbology changes, whether or not you're dealing in the concentration basis or the pressure basis, that all is reflected automatically. It grabs the right symbols, and that the choice of symbol here for the equilibrium constant is dependent upon what was passed in. Since the equation that was given didn't have any states of matter, it defaults to the concentration basis. But if we had, for example, a reaction of gases and we passed in their phases, then rather than working with concentrations, we'd be working with pressures, and this would change to K sub P. All of that done automatically based on the information that's given. So again, automatic answer key generations for a variety of chemical problems. And you're probably asking, well, what exactly does that all cover? And this is a growing area of tools that we're building for chemistry. Our chemical conversions have the largest amount of support, not surprisingly, since they found they are the foundation upon which many other calculations and chemistry problem solving is built. And then we have molecular properties recently. We've got kinetic expressions, equilibrium expressions. We also have quantum chemistry, orbital diagrams, counting the number of valence electrons for a particular individual atom. And our next area to tackle is the one that's small, and that's the acids and bases, and doing pH calculations on chemical solutions. So hopefully, as we're broadening the breadth of chemical topics that we cover, and then simultaneously digging deeper into each of those topics with the types of problems that we can solve, the answer key generation will be very helpful for you in your classroom environment and for your students to see where they went wrong when they did the problem themselves. So we've talked about accessing data. We've talked about doing answer keys. We've talked about getting collecting all this stuff inside of a notebook. But now the last sort of area that one needs for teaching chemical concepts and molecules in general is to be able to visualize. And that is a long-standing stumbling block for students of all ages when they come to chemistry, because molecules are microscopic and many of us are tactile, and we have a need to see in 3D, but unfortunately not everyone can see in 3D as well. And during the pandemic and times when you may not be able to have your students interact with a model set or the various sundries of kits that abound to be able to do molecular structure, we think that doing things in a notebook can be very helpful for that. And as I'll show in a moment, the notebook allows three-dimensional renderings that can be visualized from anywhere, and you don't necessarily have to have the software. You just need an internet access and a web browser, as we'll show you. So we have a molecule builder. We've talked about the entity system, which allows access to molecules that are in the knowledge base. But what if you want to get another molecule, or you want to have your students start by drawing a molecule of interest and then using that computationally? Well, molecule draw is your friend and allows you to do just that. So molecule draw is the function. And when you execute it, it's going to load a new window that I'll bring over. And this is the molecule draw window. It's a graphical user interface that allows one to choose the element of interest. And we have some of the common ones listed there on the side, but we have full access to the periodic table. I'm going to choose phosphorus, and now phosphorus is selected, or we could go back to carbon. And by clicking over here in the pane, you get a carbon with its valence filled out. So we get a methane. And we can start adding more bonds to that. So we'll go that way and add one more carbon. Maybe we'll do a double bond. And then we'll come back and do another bond. I'm also going to go over, I'm going to take fluorine and put that on the end. And so now I've got a fluorinated carbon group. And as you'll notice, so it defaults to the standard notation used in organic chemistry where the hydrogens are not shown, just so that you notice. And I'm going to redraw that, clean it up a bit. And now I've got the structure that I wanted. And you can keep building out things larger than what I've got here, but for the moment we'll work with this. So I'm going to hit return, and that will take our drawing, convert it into a molecule structure, and save that to the variable mole, which is now turned green. And here's our molecule object, and we get a structural picture, 2D structural picture. We have the formula. We get an atom count and a bond count, and if we click on the plus sign, we get the identifiers, the smile, and the inchi key, which are both used quite a lot in chemical informatics. But more importantly is the atoms and bonds and the formula for our uses in education. So now we've got this molecule, and now we can start doing things with it. We can start visualizing. Well, if you want a 2D plot, then that's molecule plot is the function that you want to run. And as you see, the structure that was here in the gray box for the molecule object is now accessible here. And we can, enlarge that if we want and access any of the other options that one can do with a standard graphic. Now, 2 dimensions is helpful, but 3 dimensions is what we were after because that's the place where people struggle. Many non-chemists don't go into chemistry because they just can't visualize what this molecule looks like. And so we have molecule plot 3D. Arben showed us this function a bit last week when he was showing off the map function, and I'm going to use the same syntax here and bring up the 4 different ways that we have rendering for molecules in 3D. So we have the classic ball and stick, and then we have a tube rendering, and then we have the wire frame, and the space filling. Now, these are all rotatable, interactive 3D graphic objects ready to go right then and there. So the students can, interact with them, get the view that they're looking at, interrogate the structure a bit. In this case, compare the different representations. You can have deep thinking questions on what information is carried about between those different representations. One of the things that I like to do with my students is have the 2D and 3D representations side by side so they can see how the 2 different bits of information are being conveyed through the structures. And so we have a function for that. And remember when I talked about the Wolfram function repository, we're going to use the function called molecule view, which is there. And we get access to that with the function called resource function, molecule view. And then I'm going to pass it this molecule. Note that this is a full IUPAC name with all of its gory, lovely syntax. And you just pass it right in. And what happens is it goes and finds the resource, it pulls it down from the function repository and loads it into your notebook and spits back the results. So Arbin had shown, if I remember correctly, that you can use the manipulate function. So underneath molecule view is a manipulate function that is then building this interface that gives us the 2D and the 3D structures side by side with controls over the rendering. And so you can, as I said, hydrogens are often hidden to simplify the structure by default, but here we have the option of turning them on or off in the two. Notice that it's adjusting both structures at the same time. We can change the rendering of the 2D or, of the 3D, the various representation that we might like. And we can do bond highlighting so that we can help visually get the students to see the different structures side by side and realize, oh, well, maybe I need to rotate this a bit to make these two look a little bit more similar, and see how this flattened structure here is really this bridge laid down in 2D rather than in 3D. This is great if you have a notebook and your students have access to that technology as well. But if you're teaching in an environment, maybe you're doing a homeschool environment or some other situation where the students don't have access to cloud technology or the notebook technology, and you would still like them to be able to interact with 2 and 3D graphics, this is where publishing to the cloud, you as the educator can have the tool and then make it available through a website, which is running Wolfram Tech in the background and rendering the molecules. So I'm going to show you how to do that, but before, just so that you follow along, what this means is we're going to copy the bit that we want to share with our students. I'm going to copy the output from here, and then you publish it to the cloud, get a URL, set the permissions, so you can restrict it to either just your classroom and with a password, or you can open it to the world, hit publish, and then it's just a matter of disseminating your URL. So I'm going to pull out of full screen mode for the moment, and so that adjust things just a little bit. So I would like to be able to share just this final molecule view. I don't want the students to have access to the function in the document that I'm going to create, because I want them to stay focused just on this molecule. If you wanted them to have access to the resource function and be able to change what they're visualizing, you would copy both cells. But I'm just going to copy the output cell and go over to a new notebook. And bring that up here. And so then I'm just going to paste it in. It's a little bit smaller because the notebook that I'm using for the presentation is enlarged so that it shows up well. But as you can see, it's still got a working interactive molecule viewer. So I'm going to leave that there and then go up to the menu item and hit File, Published Cloud. You'll get another dialog box that should pop up looking like this. So it's initializing it. And here you can specify a name or do an automatically assigned URL. I'm going to do specify a name, live demo. And I'm going to allow everyone access. If you wanted to password or protect it, you'd click this box and put in a password that you would then need to share with your students. Hit publish. It'll go ahead and push this up to the cloud. What's happening is that this notebook is being generated and rendered into the Wolfram cloud and attached to a URL, which will show up in just a moment. And it's formatting the notebook contents because there's a lot of graphics, and so it's thinking what shows up in the cloud is this. And so I've pasted in the address, which was, the live demo.notebook. And this is, chemistry team published. So that's just a standard URL. And what you see is what you get. This is the interactive manipulate. I am not signed in. You can, because we made it available to everyone, anyone can click to the notebook. In fact, I can copy this. But what this allows you to do now is you can do the full manipulation with the molecule view in the cloud on your mobile device or in a notebook, in a web browser at your desktop. So all of that is now available to your students without having notebook technology in their pockets. You can design these things and have it accessible to them wherever they are, which is pretty nifty, and definitely beats the ball and stick models that we used to use back in the day. So that's using a resource function and visualizing in 2 and 3D side by side, along with publishing to the cloud. Now, I published to the cloud this cell. You could publish the whole thing. In fact, the whole notebook could be put up into the cloud for students to look at and interact with. And that's what we're going to get to next. So we've got all the bits, but now we can visualize molecules, we can get data, we can get access to that anywhere for the students. Now we want to glue it all together into assessments. And so the last thing that we haven't talked about yet were the manipulatives, those interactive demos. These are all contained in the Wolfram demonstration project. And if you're in a Wolfram Alpha mode notebook, which is a newer spin on the old concept of a notebook, you can get access to that through just the natural language of the name of the demonstration. So here I've typed in visualizing atomic orbitals, the demonstration, and I get a link back to that demonstration. I've cut and pasted that demonstration here so that we can interact with it. And this is an atomic orbital visualizer, and I've loaded up the favorite orbital that I like, the FZ cubed, because I do actinide chemistry. But you could pull up any function of the orbitals that you want, move over to a D orbital, and it generates and updates on the fly. And so you can imagine building an activity around this manipulative to get students to tease out different information, to see shapes, to build, connect this to VESPR concepts and connect it to molecular orbital diagrams that come later in the curriculum. If you're in a Wolfram Alpha mode notebook, we have access to these demonstrations by clicking on the Browse Demonstrations button. And what that does is it brings up another notebook that has the Wolfram Demonstration Project content right here in the notebook. And so I clicked on the physical science one. Let me show that. Click the button. It brings up another dialog. And so I had already clicked on the physical sciences, and here's the notebook that you get. Now we're chemists, so we're going to click on chemistry, or at least I am. I know that we're not all chemists in the audience, but you can click into one of the areas and immediately get access to the notebooks containing the demonstrations. And if you click on one, the full notebook pops up and you can start interacting with it. I'm going to put this away since I cut and pasted a couple out to show you already, and we'll close this menu from the top up here. The other demonstration that I pulled up was an electron configuration browser. So it has a periodic table and a slider to change the atomic number. And so you can move through the periodic table looking at a visualization of the electrons and the orbitals that they reside in, along with some other information. Notes that for the lanthanides and the actinides, a group is not defined, and so that's showing up with the appropriate missing, not applicable statement. So we have a huge collection of demonstrations that can be used in your activities, ranging from simple things such as moving along the periodic table like this electron configuration browser does, to much more complicated things such as titrations and gas law experiments, etc. So with those demonstrations, they form the last bit that we need to start doing real real-life chemistry activities in notebooks, either in the classroom in a group environment or possibly in a remote learning environment inside of the notebook. So I'm going to show you some examples of problem solving. I've chosen a few from the collection that we have in the Wolfram Alpha Notebook Edition notebooks. Again, we have a new button up here called Browse Starting Points. And if you click on that, you get a menu. We have a collection of examples by content. If you click on the chemistry button, a new dialogue, a new notebook, actually, not a dialogue, pops up, and you have access to the 8 notebooks containing over 150 examples. I've, again, chosen a couple of those that we'll show you. We'll put away the notebook here. The enthalpy of reaction can be computed by looking at bond energies, by counting the number of bonds that are formed and broken in a chemical reaction. And here we have an example of that and how it would look in a natural language environment where the student is putting in English and the notebook is then converting that to Wolfram language and spitting out results. So we can start off by balancing the chemical equation. And again, these are doing Wolfram alpha calls in the background and pulling them up live. So here I have an example that builds on gathering data, storing it into a variable, and then using that variable later in further computations. So we are going to build the mass spectrum in reverse. So rather than collecting an experimental spectrum, we're going to take the isotopic abundances and build the spectrum. So we grab the stable isotopes. We then get the properties that we need. And again, what you can see is that the natural language is converted into the Wolfram language, and then the output is given as well. So if you're in an environment where you need to teach calculations and programming a bit, you can do that. Or if you don't, you can hide the language and just go from the natural language to the results. So depending on your curriculum, you may not want or may not be concerned with showing the programming aspect, but that's there if you need it. We grab the information, the atomic mass and the abundance for the rest of the isotopes, store it to variables, in this case B and C. And then with a natural language, you would do list plot. With filling, the filling gets us the lines in our stick diagram, and that converts it to the language and spits out the plot. Now, anyone that's done chemical education knows that this is not a completely valid plot. It doesn't have a title. There are no labels on the axes. And so you can use the suggestions bar to set that using, we click on more here, you can get access to different things. And so you can set the axis label, the plot label, and get the spectrum that you want. And then at the end, the students would want to clear their variables in their notebook. In the interest of time, I'm going to skip over the reaction order example, and we'll go on to something a little bit more complete. So you can see how you can do multiple calculations, storing variables. We've had the manipulatives, all that stuff. Well, here's an example of how to pull it all together into a full-blown activity that you might deploy both in an online classroom or in a hybrid classroom. Have the usual bits of prerequisite concepts. This might be more important for the instructors rather than students, but it's there. A section for the learning objectives of what this activity is going to strive to teach. If you're new to doing electronic activities, you're going to want to always have an academic integrity statement, clearly laying out what the students can or cannot do when they're working on the activity, and have them a cell to type their name in, acknowledging that they've read that and understand it. And then we get to the activity. Again, I've had this filled in so you can see what it would look like after the student has processed the activity, but these output cells would not necessarily be here in what you would disseminate to your students. And again, as I said, when you're moving to electronic activities, you're going to worry about trying to have assessments that are deeper thinking rather than regurgitative, because the data is now being coming from the database. So here you just ask for a periodic table and boom, you get one. And then you can go and ask for more details about that particular element, in this case tin, and then ask thinking questions about it. What's another name for the electrons, number of electrons in a neutral atom? And you have your input for the students to type their answer. Be sure to give full instructions, otherwise you'll get Twitter speak, which may or may not be what you want for grading. Continue on down, with questions, getting data, getting, in this case, different representations of the electrons in an atom. So you have the full electron configuration, and then we go down and compare that to the short electron configuration and the Lewis symbol for the atom. Ask the students to think about those three things, and compare and contrast the information contained. And then we go back and have them think further about an orbital diagram. And here, we pull up the steps of how to build an orbital diagram. And again, here's where we're using the step-by-step results here for an example. And it shows how to do this. You could add, include this here and then maybe have them build for a different atom for your activity. But here I had them do it for tin. And so steps you through building everything up, following the Aufbau principle, the Mandelung rule, and building the orbital diagram. And then it's already off the screen, but there's an activity asking, how does this compare to the other representations that we've looked at? And finally, we circle back to the electron configuration browser from the demonstration project and ask them to think about this representation of the same information about the electrons in an atom and compare to the previous things, and then ask them to choose which diagram or representation they feel is best, and then defend that using chemical concepts and proper terminology. So this is an example of the sort of activities that one can do when you combine all the pieces together in a notebook that can be used in the classroom or deployed remotely. It's not too far of a stretch to imagine taking this further and using it in the laboratory to have data collection occur immediately in a notebook. I put an example together for an activity that we used to do in lab, the titration of commercial vinegar. And so I've got 3 different sections. I won't walk you through each of the details. It's there for you to do afterwards. There was a question earlier about precision. So significant digits are represented in the language using the set precision notation. So here we're feeding in that we have a value with 3 digits of 3 significant digits. And you can put that in with units and store it right away, and it's immediately interpreted and stored into a variable. As a side note, when you're building these activities, if you're going to be doing grading on a large number of them, it's strongly encouraged that you instruct your students to use the same variable name so that grading is easier for you or your grading assistants. But yeah, so you collect the data right in line, stick it in, possibly do some conversions. Here we measured in milliliters and we're converting to liters all in the same line, storing it out with the precision. And that precision is carried through the conversion. We get the rest of the data and fill our data section in. Now you can imagine there would be an intro section with all the usual explanatory details of how to do the experiment, but I've omitted that just for clarity. And then you can have the data analysis right in line. Since you've got lists of information, you can now do math on those lists. And again, here we're keeping track of the significant digits along the way, along with the units. And when we multiply a moles per liter times a volume, we keep track of the units and they auto cancel along with the rest of the calculation. So we get our results. And then in the end, for this particular activity, this experiment, you get compute the molarity, and then from the molarity, you back calculate the mass percent using a density. Here, for this particular solution, vinegar solution, we have density information for a variety of molarities of acetic acid, and we can pull that out from the knowledge base and do the calculation by hand, or you could have the student use the tool to do that immediately. The conversion utility inside of Wolfram Alpha will go do that conversion for you, keeping track of precision, and then clearing your variables. So hopefully that gives you a very brief overview of what one can do in designing classroom activities and laboratory activities where calculations and computations are right there in the notebook, next to the data collection, possibly right next to instructions for the experiment, along with spaces for the students to respond with full thinking questions.